More experiments, he said no. But Brody. Brody.
You have to be sure. Outlier. Oh, sure.
All right, so today we're going to talk about surfaces of revolution. So far we've talked about 4 kinds of surfaces. We've talked about planes, nice linear surface in space. We've talked about spheres, nice equations. Spheres have nice equations. We talked about cylindrical surfaces. And you can think about cylindrical surfaces as really kind of as surfaces of translation, because you're taking some kind of generating curve, and if you think about translating it, that generates your surface. And we've talked about quadratic surfaces. And our quadratic surfaces or traces are all conic sections. Today we're going to talk about surfaces of revolution. We've worked in the past with surfaces of revolution. We found surface area. We have a way to find the surface area of a surface of revolution. We know how to find volumes of a solid of revolution. Today we're interested in equations of surfaces of revolution. And several of these, or especially these, we can visualize as either quadratic surfaces or surfaces of revolution. Not every surface of revolution is going to be something familiar, though, because it depends on how we generate them. What we want to do is I'm going to draw a set of coordinate axes, and we're going to talk about how we're going to come up with our equations. So we have some curve, and I'm going to put the curve in the YZ plane. So something like this, just some curve. And I'm going to say this is y equals some function of z. And instead of f of z, yeah, that's fine, f of z. If we look at a point here, now the coordinates of that point are 0, f of z, comma z. If we rotate this curve around the z-axis, what path does that point take? It makes a circle, right? If we rotate this around the z-axis, if we make a surface of revolution, the point travels in a circle. So we're generating a surface of revolution. And the trace of that of that curve or that surface in the xy plane is going to be a circle. And the circle, and if we project this down onto the xy plane, we get a circle. And the circle has radius of, well, this is the y coordinate of f of z. So the equation of that circle, if we think about it projected down into the xy plane, or if we think of the trace of the surface in the xy plane, the equation is x squared plus y squared equals f of z squared. Just the equation of a circle, center at the origin, and our radius is just f of z. And just so our notation matches the notation in the book. We're gonna write it as x squared plus y squared equals r of z squared, for r for radius. So that's going to give us an equation of that surface. For any point on the surface, the coordinates are going to satisfy x squared plus y squared equals r of z squared. So we can generalize this for a curve in any of the coordinate planes rotated about any of the axes. We just interchange some coordinates. So if we generalize, we get three cases. So we have a radius function, r, and we're going to revolve about the given axis. So our equation of our surface of revolution is, if we revolve about the x-axis, we get y squared plus z squared equals, we want our radius as a function of x. If we revolve about the y-axis, we're going to get x squared plus z squared equals r of y squared. And then we already talked about the z-axis case. So that gives us a way to come up with or visualize a surface. We can come up with an equation, or we can visualize a surface as a surface of revolution, and we can then pick out its generating curve in one of the coordinate planes. So let's take a look at a couple of examples. Let me go back here. Any questions about our procedure here? Okay. So we want, in this example, we want an equation of the surface. We want to revolve y equals natural, or z equals natural log of y about the z-axis. Let me draw a quick picture here. Here's my first octant. And there is the function z equals natural log y. If we're revolving about the z-axis, so we're going to revolve this this way. So we're also going to have if we revolve it, we'll have a similar curve over here. So we get this kind of funnel shape. If we revolve about the z-axis, we want our radius function. We need radius as a function of z. because we need x squared plus y squared equals r of z squared. So what's our radius function going to be? So we want this to be this radius. If we think about this curve in the yz plane, our radius is the y coordinate. So we need y as a function of z. So what's the other way another way that we can write that curve? Y equals e to the z. So a radius is the y coordinate if we're thinking about that curve revolved around the z-axis. So we could say x squared plus y squared equals e to the 2z. Is that the only way we could is this curve in the yz plane the only curve that could generate that thing? No, we could also have a curve in the xy plane that would generate the same curve. And then we would want our radius in that case. If our curve is in the xy plane, our radius would be the x coordinate, and we'd have x equals e to the z, and we'd get the same equation for our surface.
For finding the radius function, just solve for whatever other variable is present in the equation. So you solve this for y, but if it's in the xz plane, you solve it for x.
Right. So we want our function to be some function of z. And our radius, we visualize it this way, our radius is y. So we're in this plane, our radius would be x. So that would be an equation of that surface of revolution. And it turns into this kind of infinite funnel shape. Something interesting about this surface is it has a finite volume, but an infinite surface area. So if you
have a finite volume, the top just continues on.
Yeah. Help me out here.
because the improper integral converges.
Ooh.
Yeah, true.
Yeah, but I'm still having trouble visualizing it.
No, but the
Yeah,
top
it
would
does
continue to expand.
algebra stuff.
Yeah, but it approaches like that limit to where like
Mhm.
flat.
Yeah, so in the limit, that top is going to be flat.
I got
So it has a finite volume. So you couldn't fill it. You couldn't fill it with enough paint to paint the surface.
Whoa.
That's an interesting.
Trombone.
An infinite trombone, right?
Don't you
But we're integrating.
trombone.
It would keep going in the Y direction. Yeah, and the Z direction keep going forever.
It does.
Yeah, it does. I just used to listen.
Never had funny
Alright,
alarm?
what?
You ever look inside yourself? Say what?
At least.
Yeah, it's an interesting surface. If it's on its side, if it's along the y-axis, the name of that is not trombone, but it's Torricelli's trumpet.
Oh, Torricelli.
Torricelli's trumpet.
Sorry, we don't want to come.
So should we shape like draw and like say this is supposed to look shape kind of
If it's not clear, you could say, if your drawing is really bad, you can say this is kind of a funnel shape.
Wow.
All right, let's look at another one.
He's like your best friend.
Let's revolve 8x squared equals y cubed about the x-axis. We want the equation of the surface. All right, so we're revolving this about the x-axis. So what do we want our radius function to be in terms of? X, right? So let's solve for y in terms of x. We get y equals, if I do that, I'm going to write, we take the cube root both sides, so we get 2x to the 2/3 is a function of x. So we want a radius function to be a function of x. So then that's going to be our radius function. R of x is 2x to the 2/3. And our surface of revolution, y squared plus z squared equals two x to the 2/3 squared. What would be 4x to the 4/3? What does 2x to the 2/3 look like?
You got me something weird. Quite simple. What is it, Connor?
It's sort of parabolic, right?
Is that HAFF purple?
So if we were to sketch this thing, we get something like this in the xy plane, right? And I guess, so what we did, our function, yeah, that's right. And then we revolve that around the x-axis. So we get some strange looking shape along there. Haley's football. And our radius there is the y coordinate. All right, let's do one example where we go the opposite direction. We want to find an equation of the generating curve of x squared plus z squared minus 3y squared equals 0. So based on the form of this, what's going to be a convenient way to write this if we want this to be a surface of revolution? Well, we already have our coefficients on z, x, and z as 1. So we could say x squared plus z squared equals 3y squared. Isn't this the equation of a circle? Yeah. So our r of y squared is 3y squared. So our radius function, r of y, is the square root of 3y. So that would be our generating curve. So what axis are we revolving this about? We're revolving about the y-axis. So this is about the y-axis. So for revolving about the y-axis, we have our radius as a function of y. What would be what would be our equation? So this is our radius function. What would be our generating curve? X equals 3y. X equals the square root of 3y, or z equals square root of 3y. What is this surface? Well, the generating curve is a line, and then when we revolve it, we get circles. It's a cone, right? The generating curve in an axis is a line, and when we revolve that line around the axis, we get a cone. So this is a cone. So we could visualize it like this. X equals the square root of 3y is something like this in the xy plane, or z equals the square root of 3y in the yz plane, and we're revolving it about the y-axis, so we get something like that. So this is a cone. So also notice that this is a quadratic surface. So some surfaces we can visualize as a surface of revolution, or we can visualize as a quadratic surface. Sometimes it's more convenient to think of them as in one way or the other. And it's nice to be able to think of them interchangeably. All right, questions there? Okay.
Mr. Beamer, are we doing an activity or are we doing homework?
I have an exploration for us.
Mr. Beamer, we should just do homework.